Okay. So we said there could be some issues about choosing those versions of conditional expectation indicator B given G or the conditional probability of B given G freely for every B. Okay. Before talking about those pathological cases, let me give this a name, okay? When everything goes right, when this makes sense as a transition probability kernel, we call it the regular version of conditional probability, okay? So let's give this name to it. So this must be a transition probability kernel. So a transition probability kernel Q from where to where? Well, the first argument is omega, and these things are G measurable, right? This Q of B is G measurable. So as a function of omega, this is G measurable. G measurable. So it should be from omega to omega G, from omega G into the measure part. Measure part is B, and the sets B, they come from the sigma algebra F. So this is from omega G to omega F. Is called a regular version of the conditional probability something given G, namely this mapping, conditional probability, right? So if we have the following, Q of B, let me say it this way. So for each B, the function omega maps to Q of B of omega, or Q of omega of B, is a version of probability B given G. This is already what we guarantee when we pick the versions freely, right? This is a version of this, right? What is more is that for each omega, as a function of B, is a measure on F, omega F. Well, this I don't need to write because this already comes from the fact that it is a transition probability kernel. Is even a probability measure. I don't even need to write it. So being a transition probability kernel means what? As a function of omega, this is a G measurable random variable, but this is not enough. This should also satisfy the projection property. Namely, this should be a version of the conditional probability of B given G. And the other part of the definition of a transition probability kernel is that as a function of the set, it is a probability measure. It is a probability measure. Again, before talking about pathological cases, let's say we have a regular version of the conditional probability. Okay? So why are regular versions popular? Okay? For this, we're going to state a theorem, and we're going to prove it. Okay? So let Q be a regular version of probability something given G. Regular version of the conditional probability. Then for every positive measurable, F measurable random variable X, we have that when we integrate X with respect to Q, namely we look at X of omega bar, Q at omega d omega bar, and this is the value of this at omega. I can also write it this way. So X of omega bar, Q d omega bar, omega. Okay, is a version of conditional expectation of X given G. And I'm going to write it in a more intuitive way. So what is expectation of X? It is integral X dp, right? What is conditional expectation of X given G? It is X times conditional probability given G. So I really mean this because Q is my, maybe I should write in black because it is not easy to see it. So we really have the omega given G, but now this is a random variable. So this depends on omega. And this is what we mean by Q. So just like expectation is integral of X times dp, conditional expectation is integral of X times conditional P, conditional probability. Because of those pathologies, we have to be more careful when stating such a result, and that's why we use regular versions. Okay? This needs to make sense as a transition probability kernel, and now we can integrate X with respect to the measure part of it. And there is some confusion in notation because this is a transition probability kernel from omega G to omega F. That's a bit unfortunate. So we use omega and omega bar. That's a bit confusing, I know, but we're integrating X with respect to the measure part of Q. Omega bar, omega bar. Now this whole thing is a function of omega, Qx, integral of X with respect to the measure part of Q. And what we're saying is that we get a random variable out of that because that's a function of omega, and it is a version of the conditional expectation. Okay? Let's prove it, and maybe it's going to be more clear. So what do we need to show? We need to show that Qx is a version of X given G. So let me say this is for every omega, right? So let's show Qx is a version of X given G. Well, we need to check two things. First is that this must be G measurable. Second is the projection property. So is this G measurable? Well, Q is a transition kernel from omega G into omega F. And X is a X is measurable with respect to F. So this is the measure part of Q, and this is an F measurable function. When we integrate X with respect to Q, we get something that is G measurable. So by fundamental properties of kernels, we must have that Qx is G measurable. So this is coming from a theorem that we proved when we were discussing kernels, because kernel has a dual nature, right? You can use it as a measure, you can use it as a random variable, and when you use those properties, you preserve measurability. Okay? When you integrate an F measurable random variable with respect to a kernel from omega G to omega F, you get a measurable function with respect to G. Okay? So G measurability just comes directly from this type of a theorem that we proved earlier. The other one is that we need to check projection property. So let A be in G. We show that X times indicator A is Q of B times indicator A. Well, of course not. Qx indicator A. Right? Qx is a version of X given G. This is what we need to show. And we're going to do it step by step. First step is to assume X is an indicator function of some set in F. In that case, Qx is just, X, it's just QB, right? Just QB, because you have indicator of B here. This is going to give you just Q of B as a random variable. Since QB is a version of indicator B given G, we have indicator B times indicator A is QB times indicator A by projection property, namely the property here. And this is simply X, right? So this is the desired property. Because this is Qx. Okay? And step 2, using linearity, extend to simple positive X. And step 3, using mon, extend to positive measurable X. These we don't do. In other words, when we have a regular version, we may use it to calculate conditional expectations. So this is the lesson that we learned from this theorem. So we have this formula, right? Let me keep it here. And by this, I mean the regular version. So this is why it is useful, but still we haven't discussed what may go wrong about the existence of a regular version. So why don't we have that every possible way of choosing those QBs form a transition probability kernel? What may go wrong? Okay, let's discuss this. Okay, so back to pathological issues about QB. Okay. First of all, let's discuss a nice case. Nice case. So let's say G is generated by countably many sets that are disjoint, and they have strictly positive probabilities. So they partition, let me also say, disjoint, and the union is omega. They partition omega. So in that case, we may choose the version as a version of the conditional expectation of the indicator given G, which we created by the conditional expectations given individual events. So this times indicator A1, this times indicator A2, etc., etc. We did it for a discrete random variable in the first hour. We did it for this case last week. So this is simply a version of QB. This is simply a version of conditional probability, B given G, right? So we do it for every B, okay? So the collection QB defined this way is actually regular. Namely, it is, so for fixed omega, this is a probability measure on omega f. So let's check it. So why? Well, all we need to do is to check countable additivity, right? We need to show this is a measure. So let B1, B2 be disjoint sets. So we need to calculate Q of the union at omega. And hopefully this is going to be sum of QBIs. This is what we want to show, countable additivity. So let's apply the definition how do we define Q of B? Well, expected value of, well, I can simply write those as conditional probabilities, right? Given events. Let me use the probability notation. So this is conditional probability of the union given A1 times indicator A1 at omega. Conditional probability of the union given A2 times indicator A2 at omega, etc. etc. So now what is this? What is this? It is simply here, right? Probability of intersection divided by probability of A1. Probability of intersection divided by probability of A2, etc. Okay, let me proceed here. So how can you calculate this probability? BI's are disjoint. They're intersected with A1. What is this equal to? Probability of union of BI intersection A1, but BI's are disjoint. If BI's are disjoint, then their intersections with A1, they are also disjoint, right? So we can write it as sum of BI intersection A1 divided by probability of A1, indicator A1, etc. Let me skip the second term, even the second term. So what is this? Well, this is BI intersection A1. Probability of A1 is a constant, so I can just write it as BI given A1. I'm going to have another thing, right? So this is going to be BI given A2 times indicator A2, etc., etc. So if we collect all of those things, what we get is BI given A1, indicator A1, BI given A2, indicator A2, etc. And this is simply Q of BI given G by this definition. So we get countable additivity at omega. We get countable additivity, and we can also check that Q of omega is always 1. So in this case, everything goes well. We have a regular version. We concretely create a regular version. There is nothing wrong. So this is still not a pathological case. But in general, we might have issues. We might have issues. So let's try to create a regular version. Okay. So let's define Q of omega as 1, as a deterministic number, so that for every omega, we have this is equal to 1. Okay, let's pick it as a deterministic value. And for B in F, but the full set, because we're done with the full set, let QB be a version of probability B given G. Okay. So since Q of B is a version of the expected value of conditional expectation of indicator B given G, we have, if we have disjoint sets, disjoint in F, we can write it as conditional expectation of the indicator of the union given G, which is the sum of the indicators of BIs, and by conditional version of the series form of the monotone convergence theorem, this is equal to sum of conditional expectations, and this is my QBI. Okay. Issue is that this is true almost surely. In other words, we have a set omega, I'm going to call it omega BNs, BIs, okay, which is in G with probability 1 such that Q of union of BIs is equal to sum of Q of BIs at omega for every omega in this set. So whenever you have an equality about conditional expectations, this is always almost sure. I used conditional monotone convergence theorem in series form. I have something that holds almost surely. But my almost sure set depends on my choice of the sequence Bn. Okay? So let B1, B2 in F be disjoint, okay? So, in other words, for a particular choice of the sequence Bi, we have countable additivity almost surely. But what is countable additivity? Countable additivity means we must have it all the time for any choice of the sequence Bi. The issue is that we have, in general, uncountably many ways of choosing a sequence Bi. You have so many different ways of choosing a sequence of disjoint sets, and for each such sequence, you have an almost sure event. Therefore, if you take the union of uncountably many almost sure events, this is something meaningless. This might be something meaningless. It might even fail to be measurable. The union of those almost sure sets where this sequence so is a sequence of disjoint sets in F, might, let's call it omega 0, might fail to be measurable. But we need this to be measurable, and in fact, measurable with respect to G, and this must have probability 1. If we want to have countable additivity for all sequences, we must make sure that this is measurable and this has probability 1. And this is the technical issue here. There are uncountably many ways of picking a sequence of disjoint sets. For each of them, you have an almost sure event. But in general, you cannot guarantee countable additivity. In other words, you cannot guarantee that the measure part of the transition kernel works because of the measurability issue here. So you cannot guarantee that this is a measurable set. You cannot guarantee that this is in G, and you cannot guarantee that this has probability 1. That is the technical issue, pathological issue. And that's why people created regular versions. Okay? That's why people created regular versions. But once you have them, life is nice because you have this theorem. You can calculate conditional expectations using regular versions. So the last question I'd like to discuss with you is, when do we have regular versions? Is there a sufficient condition for the existence of a regular version? Okay. So when does a regular version exist? Okay, so here's the definition. A measurable space E is called standard if there is a set which is Borel in the real line, and a function f, let me say bijection, a bijection f from E to B, such that f and f inverse are measurable. In this case, we also say E is isomorphic to B. Let me say E is isomorphic to B. So that is that just came out of air. So standard measurable space means it is like a Borel subset of R, although it is not. In other words, it might be an abstract measurable space, but you can map it in a one-to-one manner to a subset of the real line, to a subset of the real line, a Borel subset of the real line. So a fact is that a standard measurable space is isomorphic to one of the following. The interval 0, 1, a finite set or the countable set N. So in other words, you have an abstract set, and you can map it to the interval 0, 1 by a bijection whose inverse is also measurable. Bijection. Bijection means it is 1-to-1 and 1-to-1 and onto, and its inverse exists. So both must be measurable. Both must be measurable. So of course, that's a very technical issue, but just to give you an idea of what standard measurable spaces are, for instance, real line is standard. Euclidean space is standard. The sequence space in infinite coin tossing is standard. Their Borel subsets are standard. So many measurable spaces that we encounter in applications are standard. There are even more. Okay. So, of course, why do we talk about that? That's going to be the punchline. So why do we talk about that? If our theorem, if omega f is a standard measurable space, then a regular version Q of the conditional probability exists. And the proof is long and technical, so we omit it. There is not much probabilistic intuition in that, so we omit this proof. I guess in every chapter, I have the right to omit one big proof. So we skip the proof of Carathéodory's extension theorem, which gives the existence of Lebesgue measure. We skip the proof of Radon-Nikodym theorem, which gives us densities and so on. And now we skip the existence of regular versions, but it is not as big and deep as the other two theorems. You can just write down a 1-page or 2-page proof, but that's going to take a lot of time. So it's technical, but not as deep and difficult as the other two main theorems. Okay. So about regular versions and so on, this is all I'd like to say. This is all I'd like to say. The content is a bit dry in my flavor because you're talking about pathological things, etc. And luckily, there is a way to avoid them. So just assume your measurable space is standard, and then you have a regular version. So there is no need to worry about that. There is no need to worry about that. But in applications, we always use regular versions because, for instance, we always calculate things like this, right? So we always need regular versions. Okay. So maybe before we go, we can look at something more concrete. Namely, we can look at the case where we look at the conditional probabilities, conditional distribution of a random variable given a sigma algebra. Okay? Conditional distribution of a random variable given a sigma algebra. And next time, we're going to look at the conditional distribution of a random variable given another random variable. That's going to be the most concrete case, right? Conditional distribution of x given y. We're going to look at it next time. Today, we're going to look at the case where we have, so let Z be a random variable taking values in some measurable space H. And let G be a subsigma algebra of F. So what is distribution? Distribution means we look at the probability that Z takes values in some set, right? This is distribution. Now we're going to make it conditional. We're going to make it conditional. And what does that mean? Well, this is just an event, right? This is just an event. So it is this event, Z in F, given G. So this is an event in my sigma algebra F, because Z is F measurable. F measurable. Z is F measurable. So we have F here. Z is F measurable, but it's taking values in some abstract set H. And we have some partial information G. Okay? In other words, in a G measurable way, we'd like to calculate the probability of landing in this set F. This is going to be the conditional probability. So Z in F given G, but this is a random variable. This is a random variable, so it depends on omega. So for, or let's say, the mapping F to conditional probability of Z in F given G, this is a mapping on G, right? On on H. On H. F is taken from H, right? From the image space, is called the conditional distribution of Z given G. Conditional distribution of Z given G. And again, we worry about versions. For each F, we pick one version of this conditional probability. Do they form a transition kernel? So let's define the regular versions in a similar way. So a transition probability kernel I call it L. So it's going to be a measurable function of omega. So it's from omega G into, now the image space is called a regular version of the conditional distribution of Z given G. If it forms a, when we look at L of F, okay, as a random variable, right, is a version of probability Z in F given G for each F in H, script H. And does it exist? Yes. We have an analogous theorem. So if Now the image spaces is standard, then a regular version of the conditional distribution. So let me write it this way. Conditional distribution exists. Again, we omit the proof. But here it's not a bad requirement. I mean, since it is standardness of the image space is usually a real line or Rn or something like that. So it is standard in applications, right? Because we said R, Rn, R to this n, they are all standard spaces. So that's not a very bad requirement. It is a very mild requirement. And finally, we should also say, why are they useful? Why are they useful? Because we can calculate conditional probabilities, conditional expectations using this regular versions. So that's going to be a theorem. So let L be a regular version of the conditional distribution of Z given G. Then for every measurable function H from H to R bar plus, we have, or let's say LH, which is the integral of H with respect to L. Okay. So omega and dz, Z here. This is a function of omega. This is a version of the conditional expectation of H applied to Z given G. In other words, we have this theorem. So conditional expectation. So without the conditional part, this is what? H of Z times the distribution of Z, right? So now we make everything conditional. We make everything conditional. So this stands for L of dz, because L is a conditional, regular version of the conditional distribution. Okay? So we have this formula in some sense. Expectation of a random variable can be calculated using its distribution. This is well known. Now this is the conditional version, conditional form. Okay. And the proof is not very difficult. I will just give a brief outline. So we can, again, go in steps. So take H as the indicator of a set. Take H as simple positive. And take H as positive measurable. So this is going to be proved directly. Direct proof. And to pass to here, you need to use linearity. And to pass to here, you need to use monotone convergence theorem. Okay. Still, this is not very concrete, because what is G? What is G? G is usually a sigma algebra generated by a random variable. So next time, we're going to look at the real applicable case where we look at the conditional distribution of a random variable given another random variable. Okay? And there we will have conditional densities, etc., etc. Okay? We're going to have some calculations next time. Okay? So, but today we're done with all the technical stuff. Okay? So thank you. See you on Friday.